Greetings to all my tech heads out there in the KevTechify nation, and if you're new here, welcome. In this episode, we're going to look at cryptography. We'll be discussing securing communications, data integrity, hash functions, origin authentication, data confidentiality, symmetric encryption, asymmetric encryption, and then finally we'll look at Diffie-Hellman. This episode is part of my series on enterprise networking, security, and automation. I'm Kevin here at KevTechify. Let's get this adventure started. We're going to talk about securing our communications. What that means is our organization needs to provide security for data that is located on our machines and when it goes across the network. First, we're not going to start by sending data around. We're going to start by making sure our data is the correct data. To start with, I have this folder on my desktop titled Important. And in this important file, I have these 6 files right here. Now, how do I make sure that these files have the data in it that they should and hasn't been maliciously changed since I last used them? That is called hashing, part of data integrity. What I can do is open up another program. For example, here, I'm going to use Quick Hash, and I can click on Files, I can click on Folders, and then I can go to that directory. Once again, that's the important folder on my desktop. And I can select that directory that all 6 of those files were in. I can go ahead then and click on Select Folder. And when I click on Select Folder, this program is going to hash all 6 of those files. It's going to look at each one of those exact bits in each one of those files, and it's going to give us a unique hash value based upon those bits. Well, what if one of those files have been altered? How could we check that? How could we check if one of these files here have been altered? What I can do is go to an individual file by clicking on Files here and then select File. I can then select my file I want to look at and click on Open. And when I click Open, it will give me a hash output. Right here is my hash output. And now, to see if it will actually tell if I change something, what I can do is I can go to this file, employeepasswords.txt, and I can change one character in it. To make that change, I can go there, open up my password or my employee password file. Here's the original one. And what I'm going to do is I'm going to add in a extra 0 right here on Dragon 00. So this is the original. This is the new one here. I'm going to go ahead and add this 0 in right there. I'm going to click File. I'm going to save it. We're going to go back into that hashing program, and we're going to take a look at how this hash is going to change. This hash right here starts with 65, ends with D463. What I'm going to do is I'm going to highlight this whole hash right here and copy it to my clipboard. So highlight it, copy it to my clipboard. Now let's go reopen up that employee password file again. Click on Select File. Come here, select my employee password file. Click on Open. And then here is the hash file based off of that file. If we look here, we can see that the hash is different. Remember, the hash ended in 463. Last 3 numbers were 463. Now we have 858. And to compare it, I can paste that old hash into this field here. When I paste it in, I get a message and it says expected hash does not match the computed hash. This was my expected hash, what I copied before. I went into the file, I made a change, I reran the hashing program. This was the new one here. And so the expected does not match the new. I guess it shouldn't be necessarily new, it should be the current hash. So the expected hash does not match the current or the computed hash. And that shows me that those values were different. All I did was add a 0 in. Change Dragon 0 to Dragon 00. And those hashes have changed. Change one bit in it, comes up with a different hash. And if we go to compare these two hashes, they are completely different. Just by adding on that extra 0 from Dragon 0 to Dragon 00. This is data integrity using hashing. What we're going to look at next is the idea of encryption. What we want to do here is when we move files from one point to another point, what we want to verify here is that when we move our files from one place to another, it's nice to know that they have not been modified using integrity. But it's also nice to know that they haven't been intercepted and viewed. So we need to encrypt these files. Now, to do this, I'm going to use an open source program called 7-Zip. A lot of you use that for zipping files, combining files into one file, shrinking down file sizes, but we can also use it for encryption. Here, inside of 7-Zip, I have it looking at that important file directory. I'm going to take a couple files. I'm going to take employee passwords and employee records. I'm going to highlight both of them and right click on them, go to 7-Zip, and then select Add to Archive. And then this will give me some options. And the first thing is to name the file. I changed it from the default of the directory name to something that would make sense to me. Here I'm going to call it secure.7z. 7z is the extension that 7-Zip uses. And then for the password, we're going to enter in super secure. This is going to be a symmetric password. We're going to use super secure, all one word, all lowercase. And this is going to encrypt these two files inside this new file, secure.7z. And in order for people to decrypt and view these files, they're going to have to enter in our password of super secure. And since it's the same password used to encrypt and decrypt, that is used as symmetric encryption. We're going to go ahead, click on OK. It's going to go through, encrypt those files. When it completes, we're going to have this new file here called secure.7z. In order to get access and view the data inside of it, what we have to do is right click it, go up to 7-Zip and say extract to, and then it'll extract it to the location here. When I click on extract to, it's going to ask for the password. This will decrypt the contents of that. I go ahead and enter it in. Here I checked the show password checkbox here. That way it allows me to see that I entered in that password in clear text. I spelt it correctly. If I didn't want to have it in clear text, I wouldn't check that box and it would show up as asterisks. From there, it's going to open up a new directory called secure. It has decrypted those files, and I can now go in and view those files right here. And if I wanted to, I could verify that these files haven't been altered in transit. That would be using the hash values. And that would check for data integrity. So cryptography here is going to provide you data integrity. provide you with origin authentication, make sure your message is not a forgery, provide you with data confidentiality, which is our data encryption, and making sure if data is intercepted, it can't be deciphered, and also non-repudiation, which guarantees the sender cannot repute the validity of the message, that they are the ones that originally sent it and they have signed off on it. We're going to go through a little recap here of securing our communications. We're talking about securing data as it travels across our network, as it travels across the internet. We're looking at internal traffic and external traffic. There's 4 elements to the secure communications: data integrity, origin authentication, data confidentiality, and data repudiation. Cryptography can be used almost anywhere in our communication process, and the trend is all communication is being encrypted. Data integrity is using hash functions to ensure our integrity. They guarantee that the message data has not changed accidentally or intentionally. What we're going to do is we're going to send a $100 money transfer to Alex. Starting off here, you're going to go there, you're going to say, okay, I'm going to pay Alex $100. I'm going to send him a money transfer. I'm going to send it there. I generate this message. When I have this message complete, I am going to run it through an algorithm and generate a hash. I'm going to send both of those, the message and the hash, to Alex. Now, let's say Alex is one of those guys who, you know him, but you don't necessarily trust him. That's why you did this hash. And somehow Alex was able to get the message and change that $100 that you're paying him and add an extra zero into it. All of a sudden, it looks like you are paying Alex $1,000. So you get the message. The message comes in. What happens is we strip the message and the hash from each other. We now run this new message through the hash program. We get our number and we compare them. They should match, right? When you send it there, you're expecting to pay Alex $100, not $1,000. That's $900 more than you have to pay Alex, so you don't want to do that. And because these two hashes are different, we're going to say, no, this transaction does not happen, because these hashes should match. If they match, I'd be paying them $100. They don't match, something changed in the message. Well, Alex added another zero. He's going to get an extra $900 from you. You don't want that, so you don't want that to happen. We have a different hash. We are not going to make this payment happen. We're going to go ahead and deny. Your data has changed. The integrity has been compromised. There are 3 well-known hashes out there. The first one here is the MD5 with 128-bit digest. Now, this is a one-way function. You only can hash it starting with the message, run it through the algorithm, and getting a number. You can't go backwards through it. It's a 128-bit hash. This is a legacy algorithm and should only be used when there's no other alternatives that are available. People have theorized that this is breakable with today's computational powers. The second hash is the SHA hash algorithm. This here is very similar to the MD5. It creates a 160-bit hash. So MD5 is 128. This creates 160. So the longer the bits here for the hash message, the harder it is to figure it out. But it's slightly slower than the MD5. And so some people use MD5 because it's quicker. SHA here, or typically known as the SHA-1, has some flaws and is considered a legacy item. You really shouldn't use that. The one you should use, the hashing algorithm here, is SHA-2. SHA-2 comes in multiple varieties. It comes in a 224 variety up to 512 bits for that hash message. There's also some next generation algorithms, and you should use the SHA-2 whenever possible. These hashes detect accidental changes, not against deliberate changes. And so if it was an accidental change in your data transmission, something hiccuped, a bit got lost, or a bit got added, your payment got increased by a zero, decreased by a zero accidentally, that hash algorithm or that hash won't match the message when it ran through the algorithm. But if somebody deliberately changes it, intercepts your message in there, changes the message, recomputates that hash number, right? So then all that hash number matches that new message that has been changed or altered. When they receive it in at the destination, the hash is going to match that message, and everything is going to look fine. So it protects against the accidental changes, but it doesn't against deliberate changes. Which means when you hash a message, it's vulnerable to man-in-the-middle attacks, and it doesn't provide security to the transmitted data. To provide origin authentication, we use a key hashed message authentication code. Now, that's a fancy way of saying we are going to take our data, run it through a hashing algorithm, but we're going to take our data, we're going to combine it with a secret key. That secret key you as the sender comes up with. We will combine the data and our secret key together. We're going to run it through our hash function and come up with our hash message authentication code. We're going to come up with a number. Then we send the message, we send the hash with it to its destination. When the destination gets it, it'll take that hash number off, it'll look at the data, it will decrypt it, but you need to know what the secret key is, so you have to share this secret key with the end to delete it. If you don't know what the secret key is, you're going to get a different hash value, and that hash value won't match the original, and they're going to say your data isn't matching, you lost integrity. And so if it matches, then the integrity and authenticity have been verified. If they don't match, the message gets discarded. If you like this episode on cryptography and you get value out of it, and depending upon the platform you're using, please click that like button, give a 5-star rating, leave a comment. Doing this supports the channel, which in turn helps me bring you more great content. Subscribe to my channel and click that notification bell. You can also visit my website at KevTechify.com for all of my details and how to get these episodes in video and podcast form. There are two classes of encryption that are used to provide data confidentiality. These two classes differ on how they use the keys. One is symmetrical encryption, one is asymmetrical encryption. Symmetrical encryption uses algorithms like DES, DES, triple DES, and AES. Asymmetrical encryption use methods like Rivest, Tremere, RSA, now symmetrical encryption, they use the same key to encrypt and decrypt the data. And so the same key is used to encrypt and decrypt the data. Key lengths are short, 40 bits to 256 bits. Because they're short, a lot of times people identify these as insecure. They are faster than the asymmetrical because they have shorter keys, less computation has to happen. They're typically used for encrypting bulk data, such as VPN traffic, where you're sending lots of data across that VPN. Typically, we're looking at symmetrical encryption here. Asymmetrical, there's two keys. One is used to encrypt the data, one is used to decrypt the data. We have longer keys, 512 bits all the way up to 4096. We even have longer keys available. Most people say at least use 1024, if not 2048. A lot of people say 512 is, with today's computational power, somebody could crack that if they really wanted to. It does take a lot of computational power. And because of that, it is slower than the symmetrical encryption counterpart. Asymmetrical encryption is commonly used for quick data transfers, like HTTPS when you're checking your bank data or your medical records. Something quick that can happen across that network. Symmetric encryption, once again, uses the same key. It's a pre-shared key. Same key is used to encrypt and decrypt the data. And so what happens here is we start with our message. We have our message here that says we have $1,000. We use our key, this blue key, to encrypt the data. When the data is being sent across the network, this is what it looks like. It looks like random gibberish. So if somebody was able to intercept their data and look at it, they would look at it and they wouldn't be able to decipher the message that was inside of it. Once it reaches the destination, we use that same key again, that same pre-shared key, to decrypt the data, and now we can actually see what the message is. And it's the same message that we started with way over here. Symmetric encryption algorithms, there are about 5 of them that are commonly used, that are referred to in today's networks. First one is data encryption algorithm, or commonly known as DES. This is a legacy symmetric encryption algorithm. It can be used in a stream cipher mode, but typically it operates in block mode by encrypting data in 64-bit blocks. The stream cipher encrypts 1 bit or byte at a time. And this is typically, because it's legacy, deemed insecure. So if at all possible, don't use DES. Triple DES is a newer version of the DES, but it repeats the DES algorithm 3 times. It goes through that encryption process 3 times. It's considered very trustworthy, and they implemented it using a very short key lifetime, meaning those keys change on a fairly regular basis. Then we have advanced encryption standards. This is a secure and more efficient algorithm than triple DES. It's popular and recommended symmetric encryption algorithm. It offers 9 combinations of key and block length by using variable key lengths. And those key lengths can go from 128-bit up to 256 to encrypt data. And that data can be anywhere from 128 to 256 bits long. So using all those different combinations, we can secure our data. Next symmetric encryption algorithm is software optimized encryption algorithm, or known as SEAL. It's a faster alternative than DES, triple DES, and AES. It uses 160-bit encryption and has a lower impact on your CPU, meaning it can get more data through there. And the last one we have is the Rivas ciphers series algorithms. Now, this algorithm has several variations, but RC4, Rivas ciphers 4, is the most prevalent. It uses a stream cipher and is used to secure web traffic and SSL and TLS data transfers. Asymmetric encryption uses 2 keys to encrypt data and decrypt data. How this process works is you have your 2 parties. Where you have Alice, we have Bob. And what happens is Bob wants to send data to Alice. Now what Bob does is Bob requests Alice's public key. Alice generates two keys. Alice generates a public key, one that they will share with anybody who requests it, and then Alice generates a private key. She does not share that with anybody. Alice's public key will be sent to anybody who requests that, and so Bob will request Alice's public key. So Alice's public key is sent over to Bob. Bob uses that key to encrypt the data. When that data is encrypted, it can then be sent across the network. It can be sent across the internet. However you want to send your data, it can be sent. It's sent and encrypted. So that way, if somebody intercepts your data and views it, it's just a bunch of random numbers and characters. They can't make any sense of the actual message. Then once that encrypted data reaches Alice, she uses her private key here to decrypt that data and see what the message is. Now, these keys here are one-way encryptions. The public key will take the data and encrypt it. The private key will then take that encrypted data and de-encrypt it. Those keys don't work the other way. Public key is to share with the public. The private key is to keep to yourself so you can decrypt that private information. Now, how do they do that? I'll be honest with you, this is why we love our electrical engineers, IEEE. They came up with these ideas, these theories. They did all the math, the calculus, the research on how to do this. We as network administrators just need to understand the idea of generating two keys, a public key you can share with everybody to encrypt your data. That data will get to you. Then you use your private key, the key you don't share with anybody. You can decrypt your data and then read the message. There are some algorithms here that are asymmetric algorithms. First one is the Internet Key Exchange, or IKE. This is one of the fundamental components of using an IPsec VPN. Then we have our SSL, our Secure Socket Layer, now implemented as a standard transport layer security. We have Secure Shell. Protocol provides secure remote access connection to network devices. You should never telnet into your devices. Telnet sends all your information in clear text. You should use Secure Shell, and that uses asymmetric encryption. And the last one here is for PGP, that is used to increase security of emails. When you go to send out an email, you run it through your PGP program and encrypts it with a key from the person who you're sending it to. Then you send them the encrypted email, so that way if somebody intercepts your email along the way, they just see random characters and can't read the content. When the email gets to its destination, they run it through their PGP program on their side using their private key to decrypt that encrypted message, and now they can actually see what the message is. Asymmetric is a lot slower than the symmetric algorithms because they're more complex, takes more computational power. They're based on factoring extremely large numbers or computing discrete logarithms of extremely large numbers. You're dealing with really big numbers. And when we say really big numbers, you are talking thousands of digits here that they have to comprehend. Typically, we use them in low volume cryptography mechanisms, digital signatures, key exchange, looking at secure traffic. HTTPS in your web browser is a great example of where we see asymmetric encryption. There are several asymmetric encryption algorithms out there. By far the most popular is the Diffie-Hellman algorithm here. It allows two parties to agree on a key that they can use to encrypt messages. So they're agreeing upon the key. Now, the security of this algorithm depends on the assumption that it's easy to raise a number to a certain power. The trick here is to compute which power was used given the number and the outcome. And so you're looking at formula, but then to figure out what the answer is, you're only given part of the formula and you have to reverse engineer it. The DSS and DSA are for digital signatures. Public key algorithm and the signature creation speed is similar to RSA, but 10 to 40 times slower for verification. This is those digital signatures. When you have to sign a document electronically, this is the method that they use to prove you actually signed it. Then we have our RSA algorithms. Public key cryptography based on current difficulty of factoring very large numbers. Once again, we're looking at factoring very large numbers. These are big numbers than you would normally not run into because they're big numbers, higher computational powers. Then we have EGAMAL and the elliptical curve techniques. These are, once again, using big numbers and how we manipulate them to invoke this type of encryption. The Diffie-Hellman algorithm is the most common asymmetric encryption algorithm out there. It's a mathematical algorithm where two computers generate identical shared secret keys without having communicated before. So they're able to generate these keys without actually communicating. The new shared key is never actually exchanged. So they don't exchange them. They don't verify that we came up with the same key. Where the Diffie-Hellman algorithm is commonly used is data exchanged using IPsec VPN, a virtual private network. Data encrypted using SSL or TLS, that's our encrypted web pages, and SSH data. Diffie-Hellman security uses unbelievably large numbers. Once again, using these big numbers that take lots of computational power to calculate. They're extremely slow for bulk encryption because of these big numbers. When you want to encrypt bulk traffic, don't use Diffie-Hellman. Use triple DES, use AES, use something else. Don't use Diffie-Hellman. A lot of times what we do is we use triple DES, AES to encrypt when we have lots of data, but then we use Diffie-Hellman to create the keys for that encryption algorithm. Here's an example on how the Diffie-Hellman algorithm works. Now, instead of using numbers and these very large, extremely large numbers, we're going to use colors just to simplify things down to hopefully show you how this works. To start with, our two devices, A and B, Alice and Bob, they agree upon a color, which would be like a shared key between them. They agreed upon a color. Both Alice and Bob agree that, hey, we're going to share the color yellow. It doesn't have to remain a secret. Anybody can see that they're sharing yellow. That's perfectly fine. Then each one of them have to decide on their own secret color. This secret color is chosen by them and is not shared with anybody. The secret color represents the chosen secret private key of each party. So Alice chooses red, Bob chooses blue. When they choose them, they're going to mix these colors together. They're going to mix the agreed upon color with their secret color. So Alice is going to take the yellow and red, mix it, and they're going to get orange here. Bob is going to take the yellow, the agreed upon color, and their secret color of blue, and they're going to get green here. Then Alice and Bob will send each other their private colors, the combination of their agreed upon color and their secret color. So Alice sends the private color of orange to Bob, and Bob sends the private color of green to Alice. So they get their private colors, then they add their secret color to it. Now notice we're not decrypting it, we're not going the other way, we're not taking the secret color out, we're adding secret color again a second time in this process. And so Alice is going to take Bob's private color of green, add her secret color of red. Green and red equals the final color here of brown. Bob is going to do the same thing. Bob is going to take Alice's private color of orange, add his secret color of blue, that also gives them brown. This brown is the same brown Alice has, so they have the same one. The result is the final brown color mixture that is identical to the other final colors. This brown color represents the resulting shared secret key between Bob and Alice. It was my pleasure to provide you with this wonderful episode on cryptography. If you like this episode, and if you got value out of it, and of course, depending upon what platform you're using, please click that like button, give a 5-star rating, leave a comment. This all helps me bring you more great content. Take a minute to subscribe to my channel. All of my socials and contact information are on my website, KevTechify.com, and you can get all these episodes in video and podcast form. In the upper right is my playlist for my series on enterprise networking, security, and automation. In the bottom right is one of my favorite episodes that I linked just for you. Thank you so much for watching this episode of my series on enterprise networking, security, and automation. Once again, I'm Kevin. This is KevTechify. I'll see you next time for another great adventure.